Hi everyone. Today we're going to continue our discussion on linear functions, but with different domain other than Rn. So last thing we talked about on the last video was we defined this linear function called differential operator. So we already showed that the differential operator is linear in the polynomial function space, but it's not one-to-one. So now we define the differential operator to be on the continuous first derivative function space, which the range would just be a continuous function. And it should be clear to you that this differential operator defined on this vector space is still a linear operator and is still not one-to-one. And if you need to, or if you think about try to do a proof, you find out that the proof is basically exactly the same as what happened with polynomials. Right here, except that, in this case, you're probably going to call the two function f and g instead, and define the f and g are both in C, the continuous, first derivative continuous function space. And then the zero element would actually be exactly the same as in the polynomial function. Notice that z of x equal to 0 is also a continuous function that also have a continuous first derivative, just like it is a polynomial function also. So it should be pretty clear to you if you try to write out the proof of why this differential operator is a linear operator. You should be able to do that just by mirroring the proof that we wrote for it in polynomial space. So that's not too exciting. So now what I want to do is define more different type of linear function for you, and then also show you why we want to do that. So here's my next example of a linear function. Suppose we're going to define C of the continuous function from negative infinity to positive infinity. Be the set of continuous function f that map from the entire R to R. Oops. Okay, and let's say we're given a function q of x where q also map from R to R, so have the same domain as, oops, I don't know what happened when I write this, have the same domain and range as f, and we also know that q of x is continuous. So technically speaking, q can be any one function inside C. It can be any one function inside C. Okay, and of course here we would choose that we don't want to choose q of x to be 0 because, well, it doesn't mean that it doesn't work with 0. It's just that you make everything 0, so it doesn't really do much. It's trivial. So here we want q to be some kind of non-zero continuous function. Okay, so now what we're going to ask you to do is, what we're going to try to do is the following. I'm going to ask you to see if you can do this. So show that if I now define a linear operator q of f of x, which is equal to q of x multiplied by f of x. I want you to show that this is a linear operator. Now, one of the reasons why we call this a linear operator but not a linear function, because we already have an input that's a function. So it gets confusing when you do that. So here we define it to be an operator, operate on a function. And in this particular case, this linear operator q will multiply whatever function we plug in by another function, q of x. So in this case, I'm going to go and call this linear operator q. Would go from C, negative infinity to positive infinity, to C, negative infinity to positive infinity. So the domain for this linear operator would be a continuous function that has a domain that's negative infinity to positive infinity, and will give out a function as a result which also have a domain of negative infinity to positive infinity and is also continuous. So if you want to pause for a little bit to try it out on your own before you continue the video, you should, but before you do that, I'm going to go ahead and kind of tell you what you need to do. So to show that this q of f of x is a linear operator, what I need to do is to show this is true. Show that if you put in a times f of x plus b times g of x into this linear operator f, it wind up being the same as a then q of f of x plus b q of g of x. Okay, so if you want to pause the video, go ahead and pause the video for a little bit and just try to see if you can do that. And I'm going to continue the video. All right, so to show this is true, all I have to do is just go for it and see. So here's I'm going to go ahead and do my right side. I'm sorry, I can't tell left from right. On my left side. So what does the linear operator q does? Well, q basically multiply the entire input by the function q. So like that. And so based on what we know about function, now remember, even though these are all functions, well, actually, okay, g of x, f of x, and q of x are all function. But then because they're function in the real numbers, so therefore it still follows some of the real number property. Like in this case, the distributive properties still apply. So what I'm going to do is I'm going to distribute. And because I'm basically, even though I'm multiplying three functions together, but they still follow the rule of multiplication with real numbers, that means I can now rearrange how to multiply these three things together in such a way that I can multiply two of them first. And because multiplication is commutative, I can say, well, in this case, I can say this is the same thing as a times q of x, f of x. And we'll group q of x times a of x together. And I'm going to say b times q of x, g of x, and also group q of x plus times g of x together. And now you should be able to see that q of x, f of x is nothing more than a times q of f of x. And then q of x times g of x is nothing more than q times g, q of g of x. So therefore achieve what I want to prove. And I know it's kind of weird because we're actually doing function on another function. But we're not doing it like composition or things like that. But we actually can define different ways to define our function that can be applied to as another function. One of the main reasons why we call operator instead of function because of the confusion. So here I can actually do an operator on a function, which basically operate on a function and create a new function from it. So in this scenario here, this shows that we do have a linear function. So now the question, why do we go through all this trouble? Well, remember, the basic idea here is for us to kind of use this concept of linear algebra to try to apply it to different vector spaces as function, and then use that to solve differential equation. Because remember, I told you that the solution set to a differential equation actually forms some kind of vector space or subspace. So in this case, I can actually combine the two linear operator that we figured out and together. So if I combine the differential operator d of f of x and the operator here q of f of x, we can now form differential equation that would now allow me to understand that our differential equation is actually some kind of linear function in disguise, and therefore allow us to use our concept of linear function to solve it. So this two operator combined will allow us to form a very simple differential equation, something that you know how to solve last year. So suppose I take these two linear operator and just say set them equal to each other. then what happened is this formula right here simply just turned into this differential equation. Which is definitely a differential equation because it required the derivative of an unknown function f, because remember q is given as a specific function that we know, and the derivative of a function, unknown function f, relating to the function f itself. All right, so that's basically how we are using this concept of differential linear functions as well as vector spaces together to kind of redefine differential equation in such a way that we can use our knowledge in linear function to help us solve those equations. And of course, also find it as a way to kind of express a solution set. So now that this is done, now let's try to talk about something more interesting. So now that we have this linear operator, is it possible to combine linear operator together the same way as we combine function together? As a matter of fact, if you think about what we talk about in 3.1, we define linear function, and then we define ways to combine linear functions together. And one of the more powerful ways to combine linear function together is through composition. So now the question is, can I also do composition with like operators like this, linear operators like this? So let's talk about how to do that. Compositions of linear function. So if you recall in 3.1, we learned that when we define linear function from Rn to Rm, they can be written in matrix form, and then when we form linear composition of them, they just become, the matrices just get multiplied together, which is a very nice and simple way to form composition, is through multiplying the matrices. But there's a problem here, because this kind of operator that we have right now in 3.3, they are not definable by matrix. Reason why? Because they are defined on a different vector space, not a vector space from Rn to Rm. So therefore, we cannot really represent them using matrices. So how are we going to work? Well, let's find out. So we call from 3.1, if you have a function f and a function g, you could form a linear combination of them, provided that the domain and range will somehow allow you to connect them together. So imagine the following. Suppose I have a function f that go from Rn to Rp, and let's say I have a function g that go from Rp to Rm. And let's say function f is given by some kind of vector, some kind of matrix multiplication of a times vector x. Okay, and then g, I'm going to just use vector x also. Notice that this vector x is in Rp while this vector is in Rn, but I don't really feel the need to use a different letters. Would equal to b times vector x. Then combine these two together. Now notice the way that is written, there's only one way to combine them together, and that would be a vector first go for f, so it would be in Rn, and turn by function f turn into a vector in Rp, and then that vector in Rp will get put into g, and then it would get pop out as in Rm. So therefore the composition is actually G composition F, which go from Rn to Rp and then Rp to Rm. And in this case, G composition F of vector x is just basically equal to b times a vector x. Notice that it works out because in this case, the matrix A in this case is a P by N matrix, and matrix B is going to be a M by P matrix. So when you do B times A, it will be M by P multiplied by P by N, and therefore will form a M by N matrix, which work out perfectly for the function g composition f that we define. So that's nice and simple. But that's, remember, is go from Rn to Rm. But ours go from like continuous function space to continuous function space. And because of that, we won't be able to form a matrix of that. So how does that work? Well, the concept is exactly the same and is actually summarized in this theorem. So theorem 3.3.4, it states the following. Let's say if a function f go from some vector space u to some vector space v, and let's say function g go from vector space v to some vector space w, and let's assume that both of these are linear. So notice that in the example at the top, because I can define both f and g as a matrix multiplied by a vector, that automatically means that both f and g are linear. And since the composition also formed by a matrix times the vector x, that would imply that the composition is also linear. So that's pretty clear. But when you're dealing with function from a different vector space, then that's not going to be as clear because you're not using a matrix representation. So theorem 3.3.4 basically confirms what we suspect. If you take a linear function and another linear function and you form a composition between them, the composition must also be linear. So then their composition, in this case, the composition have to be formed the same way. G composition F would define from the vector space U through V to W. Okay, and this composition is defined just like how we define normal composition by G composition F of X is equal to G of F of X. And it is also linear. So if you form a composition between two linear functions, the result must be linear. Now, what's the interesting thing about it then? Well, the interesting thing about it is the following. So imagine the following. Imagine if I take a function. Let's say we define a function, let f be a function that defined from v to v. It defines a function that goes from itself to the same exact vector space. Okay, so if that happened, so let's say f of x is a function that maps from v to v. Let's say f is a linear function with the same domain and range. So in a sense, I want this function to kind of have closure. Okay, then what does that mean is that then I can now define f composition f. So in this case, f composition f will basically take v to v, then to v again. So therefore just basically v to v. And notice that this composition is the same type of function as f because also mapped with the same domain and range. So therefore we can actually repeatedly do a composition by doing the following. Well, obviously one thing we want to do is to simplify the notation first. So if I do a composition f of f, then what I'm going to do is I'm going to refer that to f squared. And with that being said, now I can actually do f of f. And now the idea here is the following, is instead of doing a composition with three functions, notice that because in this case, the function f is a linear function that have the same domain and range, so therefore if I form a composition of f with itself, it would still be a linear function, and it would still have the same domain and range. That means it has closure. So therefore now, if I have to do three of them, I can just simply combine two of them first, and then do the third one. So meaning, when I do this composition, I'm either doing it f of f of f or f of f first, then of f. Either way would allow me to combine three of them together without any issues, because each time I'm doing it, I still have the function that have the same domain range and is also linear. So therefore, what do we call this then? Well, simple. We call this f cubed. And so this process can go on and on to as many as we want. Let's say there are n of these. Then that just become f to the nth power. Now, so why do we want to do that? Well, of course, here, I mean, I'm sure some of you already probably noticed why I'm doing that. The reason why I'm doing that because of the differential operator. So now consider the following. Now consider a differential operator. That means d of a function f is equal to f prime. And we know this is a linear operator. And it defines a linear operator from a function space to another function space. Therefore, I can do the following. Now, of course, here's a tricky part. Okay, is to understand how the operator work. In general, if you don't want to think too much about it, basically meaning the following. Okay, so I'm going to try to write this out first. So if I do that, then what happens if I apply a composition? Oops, I don't like that the way that look. Let me just try again. D of f of x. Then what does that mean? Well, that simply just means d of f prime of x, because d of f of x is f prime, and then we all know what happened when you take the derivative f prime, that becomes f double prime. And then if I do d of f of x, then that would mean just d of f prime of x, and that's just d of f double prime of x, and that just becomes f triple prime of x. And then this process can go on forever until eventually we can define d to the nth power. Oops, actually, I don't need a parenthesis here. I'm going to say d to the n power of f of x, and that just becomes f to the nth derivative of x. Now, some of you might notice an issue here, because when we define our differential operator, we want to define our differential operator from a first continuous first derivative function space to continuous function space. And you're correct. So that would be what I want to do. If I want to define d, I will have to define d to go from C1 of some domain, I'm just going to put x, whatever that domain is, to C of the domain x. So that will allow me to guarantee that if I take the differential operator and differentiate something that have a continuous first derivative, I will get a continuous function. Now, for the most part, we actually not too care about this for multiple reasons. Number one, what if the function is not continuous or doesn't have continuous derivative throughout? Well, then what we're going to do is to fix the problem is to define the define the function just in the interval with the continuous function. So therefore, meaning that we'll restrict the domain of the function so that it has a smaller domain that will make it continuous and has a continuous first derivative. But if you're truly concerned about it, you could also simply do the following. In the second case, let's say I'm going to do a second derivative, then what I'm going to do is I basically go define it to be from a continuous second derivative space. And then therefore when I take the first derivative, it will form a function in the first continuous derivative function space. And then when I take the second derivative to that, then that would form a continuous function. And so how to deal with triple derivative? Same thing. We're just going to define the function d in function that have 3 continuous derivative. And then I can continue to define that so that my d to the nth power, d squared, d to the third, would work from a n continuous derivative function space to the continuous function space. And once again, don't worry too much about if the function doesn't have a continuous derivative, because what we're going to do is we can always restrict the domain of the function so that it would be continuous in the domain that we choose, along with the derivatives or higher order derivatives of it being a continuous function. So therefore, that's not a big concern as long as we can define a domain that will satisfy that. So now the last thing I want to talk about for today, the video is about 26 minutes already. So maybe we'll just talk about one more thing, and then we can end today's video with, okay, is the following. Is theorem 3.3.5. So now that we know how to form composition between linear functions on domain other than Rn, now we can talk about what if we want to combine function in different ways. Well, there are only 2 different other ways that we want to combine linear function. Or, I'm sorry, more accurately, in linear operator. That would be the following. Let's say given 2 linear function. So when I say 2 linear function, then that means linear function, or you can think of it as linear operator on functions. F and G. Let's say F and G both have the same domain, which is some vector space V, and map into some vector space W. And if they're both linear and they both have the same domain and range, then what I'm going to do is saying, I can tell you that if I combine these 2 functions together through addition, their sum would still be from the same domain to the same range. And if I multiply a linear function by some kind of scalar, it will still force it to be the same domain and range, and they also both result in linear function. Now, why is that important, or what do we going to do with this? So we can definitely do a quick proof of this, but I'm going to actually leave it to you to do that. I'm going to ask you to try to prove that if you do have 2 linear function, what would happen to the sum and a scalar multiple? So in this case, the number alpha is a scalar. And I'm going to leave it up to you to try to prove that. And if you want me to go through the proof with you, you can ask me in class and I'll show you how to do the proof. But what I want to actually talk about would be, how do I use Theorem 3.3.5 as well as Theorem 3.3.4 together to actually put together differential equation. So imagine the following. And that will probably be the last thing I'm going to show you in this video. So hopefully this video is not going to be too long. I'll try to finish up really quick. So suppose I have the following. Suppose I'm going to let P of x, Q of x, and R of x be continuous functions. So these 3 functions are all continuous. So they're in the continuous function space. And let's say I'm going to let D be the differential operator, just like how we define it. So basically meaning that when I apply D to a function, it just takes the derivative of it. Then we'll define the following linear operator. So my first linear operator is L1 of some function u of x. And that would equal to p of x multiplied by d squared of u of x. And I'm going to define L2, my second linear operator, on u of x. And that would equal to q of x multiplied by d of u of x. And notice that all three of these are kind of like the q of f of x that we defined before, which we know are linear. And why is it similar? Because d square of u of x would just be a function. Okay, and it would define this in a second continuous derivative function space. Then d square of u of x would be a continuous function, which would now allow me to multiply to p of x, which would still form a continuous function. So L3 of u of x is just equal to r of x times u of x. So this is basically the same as q of x, q of f of x that we defined before. Now what we're going to do is we will combine L1, L2, and L3 together to form a differential equation, or to form a linear function. How? Well, because remember, sum of linear function remain linear. So I'm going to define this linear function or linear operator L that go from the second continuous derivative function space to the continuous function space. The reason why I have to go from second continuous derivative function space, because I have to make sure that the second derivative of u of x have to be continuous. So that way in L1 here, this operator will allow me to multiply p of x, which is a continuous function, to another continuous function, the second derivative of u of x. And that way it won't cause an issue. So in this case, how do I define L? Will be L of u of x would equal to L1 of u of x plus L2 of u of x plus L3 of u of x. So technically speaking, what is L of u of x? Well, that just means this. L of u of x is just equal to p of x times u double prime of x plus q of x times u prime of x plus r of x times u of x. And if I now let L of u of x equal to some function, then I can form a differential equation. If L of u of f of x, L of u of x is equal to some function f of x, then what we have would be a differential equation. We'll state this: p of x, u double prime of x, plus q of x, u prime of x, plus r of x, u of x, equal to f of x. Now, I know that seems like very abstract and very confusing, but how about we do this? How about I write you a specific one? There you go. Now that would be a differential equation in the function u, and it has p of x, which is sine x, q of x, which is the number 3, r of x, which is eta x, and f of x equal to tangent x. And now because I can naturally interpret this more or less like, oh, actually, I'm sorry. I can use tangent, because tangent is not continuous. Well, unless we restrict the domain to negative power over 2 to positive power over 2. So let's just pick one that is continuous from negative infinity to positive infinity. How about, I don't know, x squared. There you go. Okay? So now let me continue. So now in this case, now I can actually look at this differential equation as a linear operator equation, and then try to solve it as a linear operator differential equation, which in this case the linear operator is the operator L that we define, which is come from 3 separate linear operator put together. So that's the kind of the end goal here, is to try to do that. We visualize our differential equation not as a differential equation of a function that we don't know, but rather a linear operator of a function that we don't know. And then try to use our understanding of linear operator to help us solve this differential equation. I know it's confusing and it's sometimes very abstract for to understand, but eventually when we start doing more of this, you'll get used to it and you'll be able to understand how it works better. So because right now it's brand new to all of you, that's why it could be very confusing. But it will get better eventually when you work more on it. Unfortunately, I'm going to have to stop right here. This video is already too long. It's 36 minutes. All right, so I'm going to have to talk to you guys tomorrow. Okay, bye-bye.